Well, good afternoon, everyone. I hope that you're all staying safe and healthy. My name's Al Gashevsky, and I'm the chair of the Hans Liebe Fellow Search Committee. The U.S. National Committee, USNC-URSI, with the generous support of the Liebe family, has established the Hans Liebe Lectureship in Microwave and Optical Spectroscopy as applied to radio science, remote sensing, and telecommunications. This lectureship provides travel support and an honorarium for a distinguished member of the radio science community to deliver a lecture on the professional topic of their interest at each of the annual USNC-URSI radio science meetings. As many of us are aware, Dr. Hans Liebe was the developer of the MPM 93 model for atmospheric microwave absorption and refraction. This model, developed through Hans's meticulous measurements in the 1980s and early 1990s, is a standard that enables much of our contemporary propagation work in remote sensing, radio science, and telecommunications. And for those of us who knew him, Hans was also a great friend to the radio community. On behalf of USNC-URSI, I'd like to express our gratitude to Mrs. Liebe for her support of this lectureship in memory of Hans. The 8th Hans Liebe Fellow is Dr. Brian Drouin of the NASA Jet Propulsion Laboratory in Pasadena, California. Dr. Drouin received the BS degrees in mathematics and chemistry from the University of Wisconsin in 1995 and his PhD in chemistry from the University of Arizona in 1999. Dr. Drouin's background in chemistry and mathematics and interest in molecular structure and symmetry have nurtured an extensive career in molecular spectroscopy to support remote sensing observations. His research interests include instrumentation for remote detection of far infrared radiation, atmospheric chemistry, climate change and pollution, low temperature collisional dynamics, molecular spectra and structure, and instrumentation for laboratory and field studies. He has been a principal investigator for several major NASA projects involving atmospheric spectroscopy. Without further ado, I'd like to introduce Dr. Drouin and allow him to present his talk on molecular oxygen absorptions from red to radio. Dr. Drouin.
Thank you, Al. I will share my screen. So I want to thank URSI and the NRSM and the Hans Liebe Lectureship for the honor of presenting the 8th Hans Liebe Fellow Lecture. And I'll comment that I never had the pleasure of meeting Hans Liebe myself. However, ever since I got to JPL, I've seen the fruits of his efforts in action in the remote sensing community that I'm embedded in. And in many ways, the work that I do mirrors the work that he did, that he did the seminal work on. And so that makes this effort much more special to present to this at this event. So today I will give you a review talk of pretty much all of the work that I've done on molecular oxygen over my career. And this includes a number of coworkers who will be acknowledged along the way. And I've organized the work first to present the resonant line model, where we can now predict with high certainty all of the positions of all of the molecular oxygen absorption features up to 15,000 wave numbers for all of the natural isotopologues of oxygen. And that work was inspired by my training in making millimeter, submillimeter measurements and the availability of higher frequency sources that were developed at the Jet Propulsion Laboratory for space missions. And after going through those efforts, which are presented somewhat linearly in order of the publications shown here, I will then switch to the collisional phenomena, which have actually been considerably more challenging in comparison to how well known the line positions can be. Collisional phenomena are much more difficult to model theoretically and to measure consistently. And this is quite a bit of what Hans Liebe was doing in order to understand atmospheric propagation. And so that portion of the talk, I've organized it in order of the spectrum, going from short wavelength red to the longest wavelengths radio, which is some of my most recent work and is still unfinished. I will mention along the way that this is not enough to do a comprehensive line model. There is a desire to also have all of the intensities of these transitions understood to a high degree of fidelity. And so in my future directions, I'll discuss a little bit of what we'd like to do in the future for modeling the intensities. So before I move on to the rest of the presentation of these moments and papers, I have a diagram at the bottom of the screen for the uninitiated. I noticed a lot of the talks at this conference are very strongly founded in the fundamental physics, and that's exciting. This talk is more generalized, even though there is quite a bit of detailed physics in the publications. At the review level, you don't quite see that. But the cartoon at the bottom shows oxygen molecule, the two red balls that are bonded together. And inside the molecule are two magnets that I've used as clip art here. But the arrows indicate the various angular momenta we have inside this very special molecule. It is not a typical diatomic. It has no electric dipole moment, which means that its primary interactions with matter or with light are through magnetic interactions. And so when we see absorption across the electromagnetic spectrum, it's typically a magnetic dipole that is inducing the change in the electric field and the magnetic field of light, or it is, those could be electronic or nuclear spins. And so here schematically, the absorption is shown that the blue light passes straight through as if the oxygen molecule isn't there, whereas the red light is getting absorbed. So I got really interested in extending the knowledge of oxygen through the development of high frequency sources around me at JPL. I was able to get access to terahertz sources that were developed for the Herschel Hi-Fi Space Observatory, which was launched in 2009, and for 4 years made measurements of the far infrared spectrum of deep space. But those sources that were used as local oscillators within the instrument were also quite useful for building sensitive spectrometers in the laboratory. And on a later slide, I'll show you a picture of our highest frequency multiplier chain, but I'll just say that my initial training in millimeter, submillimeter spectroscopy, there was a much more complicated connectivity diagram because we had a free running oscillator like a klystron or a BWO that was then locked to the harmonics of a lower frequency synthesizer. And that required quite a bit of user intervention and control, and limited the amount of coverage you could do or integration you could do of a given feature in the spectra. Whereas these local oscillators were wide enough bandwidth and high enough power to directly use for spectroscopy, and they were harmonically pure to 20 or 30 dB, which meant that we could take spectra without having to do any tuning other than just computer communications with the synthesizer. And so that part of the spectrometer became autonomous in the early part of my career, and enabled us to really focus on what was happening with the gas, which for oxygen, we were doing line shape measurements. So we were temperature controlling, pressure controlling, and also later I'll show you the effects of Zeeman modulation. That's the wire wrapped around the cell here. But the simplest measurements you can do, if you frequency modulate the synthesizer, and then you demodulate that at a lock-in amplifier, you get a characteristic 2F line shape whenever you pass through a narrow absorption feature. And so this paper from 2010 shows the highest frequency measurements we were able to make at that time. The oxygen lines are fairly weak compared to many of the absorptions in the terahertz. And so you do see quite a bit of noise on these measurements. And also one of them shows that, we also battle against the baseline in these measurements, the background radiation that's bouncing off of optics and walls and creating other features that are not related to the gas. And so when we analyzed that data, we used a molecular Hamiltonian, the software developed by Herb Pickett, my mentor, and another oxygen developer, a contemporary of Hans Liebe. We discovered very quickly that we could develop a Hamiltonian for each one of the isotopic forms that included all of the spins. This is the rotational part, and then the electronic spin, the rotational spin coupling, spin-spin couplings, and then if you, in the oxygen-17 case, you can also have the quadrupolar coupling of the nucleus to the electric field. Those features all were able to be transformed into a isotope-independent Hamiltonian. This is pretty regularly done for diatomic molecules. Dunham back in 1930s developed the formalism, and it was honed over the decades to have the correct isotopic corrections so that you could minimize, so you don't need a rotational constant, a different rotational constant for every isotope. Instead, what you need is this independent rotational constant that's independent of mass and two corrections which take care of every isotopic form that you can generate. And by using this formalism, we were able to dramatically reduce the number of free parameters in fitting the states. We applied the physics to the excited states, and then we're able to apply the model to not just our own data recorded in the terahertz region, but also to all of the data that was rotationally resolved that we could find in the literature, which includes transitions up to these electronically excited states, which some of them get pre-dissociated, so we had to be careful, and there are perturbations up there. But all of the transitions that we typically think about for atmospheric purposes are related either to the ground state or to these first two excited states, which involve spin reconfigurations in the pi electrons, and hence are at much lower energy than the electronically excited states up above 4 eV. And so this chart is not ours. We took it from Slanger, who actually analyzed quite a bit of rotationally resolved airglow data from the atmosphere. And these are natural emission features that connect higher lying states. And so we used quite a bit of that data. And we also used literature data from a number of different types of spectrometers. And Chen Yu, who led this effort, she is the one who actually did all of the work of incorporating this information into one model. She calls it the grand fit. And it is grand in terms of spectroscopic efforts. And the best way to describe the effort is a connectivity diagram where the ground state, it runs along the entire bottom of this chart. And then each one of these numbered boxes is a level that we included in the model from a given excited state. The numbers are not physical, they're just counting numbers for our purposes. But the states are vibrational progressions vertically here. So you go from the ground vibrational state in a given electronic state up to excited vibrational states. And you can see that many of the connections don't feel the ground state. So you have to connect them through a model like a Hamiltonian. And this effort resulted in a model that was so expansive and precise that we started to wonder whether there was need for any more measurements. And so one of the things the model could do was it could predict not just the positions of terahertz lines, but the positions of isotopic lines for excited states of oxygen in the terahertz that had never been measured. And so this is an oxygen singlet delta line measured in absorption in a plasma cell shown here, where we have oxygen sitting statically in between a hollow cathode and a hollow anode, and we can pass radiation through the length of this cell. And when you induce current through this system, it glows. The white glow is characteristic of the atomic emission of oxygen, but the physics inside the system are cycling oxygen through atomic states back to molecular states, and it passes through these excited molecular states. If you do main isotope discharges, you get very strong signals from oxygen 16 in its singlet delta state, and these have been done before. We did not make much of a difference in the literature for that state. However, because we had a static system, it was fairly easy to integrate for long periods of time, static discharge system. And this was an oxygen 18 measurement done in natural abundance. And then we actually took advantage of the static system and started putting isotopically enriched forms of oxygen into the system and integrating in the regions the model predicted there would be features. And the most interesting features by far are the spin multiplet spectra of the oxygen 17 isotopologues. Shown on the right here is a progression from J9 up to J13, where the spin orbit splitting from the J5 halves nucleus for one oxygen is coupled to the orbital angular momentum and producing a sextuplet. The spin of oxygen 17 is 5 halves, so you get 6 different states for the main transition, which is a delta F, the hyperfine quantum number, is the same as delta J, +1 in this case. And you can see that that progression, it bunches up and becomes slightly unresolved at the highest quantum number that we measured. What's not so easy to see on the charts squeezed onto the right-hand side of my figure are these other features, which I've labeled in the J11 spectra. And those are transitions in which the hyperfine quantum number is not changing. So you're inducing a change in the overall rotation, but the spin is flipping against that. And that's less probable. and therefore the lines are about 30 times weaker. However, the sensitivity was good enough in several regions of the spectrum to analyze those. These features that block it in this region here are actually interloping features from another part of the spectrum because the sources aren't totally harmonically pure. We had to watch out for these things and not assign them to the wrong features. So I mentioned that the model predicted all of these features for us, and so there wasn't really much searching. We could just dial up the range and integrate the instrument. And so here's that trace I showed you as the best signal to noise out of the progression, and this is the measurement with a pretty decent signal to noise. Here is the model before we made any adjustments. And from my experience in spectroscopy, this is phenomenally good. Many of the features are predicted with exactly the right line position. And then you can see that if you squint, you can see they start to slightly disagree at the highest frequency feature in the first multiplet, and that's a little bit more strong in the hyperfine, the weaker hyperfine multiplet. And the reason why the model is so good in this region is that just prior to our efforts, Olga Leshishina had published infrared measurements of transitions from the oxygen ground state to the oxygen excited state measured around 1.4 microns. And they measured the isotopically enriched samples like we were doing, and they measured them at low temperature. They cooled the gas to liquid nitrogen temperature, about 77 Kelvin, which reduced the Doppler width of the features in the infrared and allowed them to partially resolve the spin orbit hyperfine features, that the same ones that are presented in this spectrum. They had to also deal with the Hamiltonian of the ground state, which is how we knew about their model in advance of their publication, because they reached out, and Shanshan Yu is co-author on my work as well as on Olga Leshishina's work. And so we basically had the model in hand at the time they were publishing, and were able to look for these transitions in an advanced notice. What we did, of course, once we had made our own measurements, was we looked at how we might improve the model. And by adding a small spin orbit centrifugal distortion term, we were able to fit the spectrum slightly better. And now you don't see those discontinuities as easily. The ones that are maybe prevalent in the weaker features are at signal to noise comparable to the level of the experiment. And so we considered this the best fit. And of course, it was only slightly better than the previous model. And so all those equations shown on the slide earlier, we basically added one higher order term and got what we needed out of the new measurements. So that gas cell that was glowing white, it was curious to me. I always thought of oxygen as glowing green because of the aurora, which is, when you see green aurora, that's associated with oxygen emission. However, our discharge was white, and I was vaguely aware that there were red emission lines of oxygen. And so I got my hands on a handheld visible spectrometer. This is ocean optics back end. Students in chemistry labs and perhaps maybe physics labs too use these handheld devices now at the undergraduate level. And typically there's a light source and a cuvette, and they can do liquid or solid state measurements. We used just the detector end, and I held it up to the side of the plasma discharge cell and saw these large features of atomic emission lines from oxygen atoms. But right next to those features was a molecular emission. You can see it's much broader than these narrow features, and it's of course at the position, the well-known position of the molecular oxygen A band. Labeling is just that it was the first oxygen band identified and basically the first absorption feature in the atmosphere identified in the 19th century. So this measurement was quick and dirty, but very intriguing. Once I saw that we could see emission at short wavelength, I just had to bring the instrument, bring the cell over to our Brooker instrument, which is a Fourier transform Michelson interferometer that typically uses a broadband light source, and we put absorption cells between that and the detector. But in this case, we used the oxygen emission as the light source. And when we lined it up in the emission port of the instrument and integrated the signal, we saw the atomic emission lines again. They're actually clipped because they go to almost 10,000 counts on this axis. And then we saw a very well resolved A-band feature and higher order features that weren't visible at the signal to noise of the quick and dirty experiment. And this work was published in 2013. We just dig in a little deeper that the A-band signal to noise was very high. We could see isotopes in natural abundance, as well as what are called hot bands, where the emission begins in an excited vibrational state and ends in an excited vibrational state of the ground state. There's also vibrational difference bands, where emission starts in the ground state of the excited state and ends in a vibrationally excited state of the ground. And there's a progression. You can think of this band here as the hot band version of that difference band. And then there's, at the limit of our signal to noise, there's another in this series of bands where you start in the ground vibrational state of the singlet sigma state and end in the second vibrationally excited state. This series, these spectra were recorded with almost a whole week of integration time. And the spectral resolution of the interferometer was good enough to see 9 megahertz precision on strong features. And then as you get down to signal to noise of a few, that the ability to measure the line center degrades to as bad as 150 megahertz. And this precision for the main isotope of oxygen was not enough to see any differences from our model. The model had predicted every one of these lines to within the uncertainty of these measurements. And most of the information for these states had come from atmospheric measurements of air glow. We were basically doing a laboratory simulation of air glow. And so that was another example of the power of the predictive power of this program, of this model. And of course, we have the isotopic species that we used for the measurements in the terahertz. So we looked also at the emission spectra of the mixed isotope features, and these spectra that shown in color are, 6-7 is oxygen 16, oxygen 17, 7-7 is 2 oxygen 17 nuclei, and so the mixtures are labeled according to which gases we put in. So this was a pure oxygen 17 sample. This one was a mixture of that sample and oxygen 18. And you see all the features are coming in fairly well resolved. And finally, we saw something that was wrong with our model. I'm showing here spectra, the positions in megahertz, shown as a difference between what we measured in these spectra versus the model. And you see that the stronger lines, 200 in my intensity units here, are all within a calibration factor of 0, and we had belief to, the deviations here are the reduced signal to noise. However, when you look at this other band, which I called the new band here, but it's the one shown on the left here, these are the A band, which isn't shown. We saw a systematic offset for both the 1618 mixed isotope and the 1818 isotope log. And that offset was 100 megahertz for one isotope, 200 megahertz for the other. And when we traced back to the source of the information in our model, these were all based on Raman data published in the early 1980s. And in that study, they also did oxygen 17, and none of those bands were showing the systematic difference that we were seeing for the 18 isotopes here. And so, we scratched our heads a bit and decided that we were very confident in our relative measurements. These were all measured simultaneously in the same experiment, and you can daisy chain things if you want and show that the positions are equivalent for equivalent species across the spectra. And so we concluded that there was some systematic errors in just some of the measurements of that Raman work, and we recalibrated it to improve our model, and we of course added this data to the model. So when you look at all the things you need to build an absorption model, this checks off the first line. We have a Hamiltonian that predicts all of the energy levels and allows us to do the positions of the lines. And then you look at all the other things that you need to build up a comprehensive model of the absorption of oxygen, and you realize that that's just the beginning. Line intensities are equivalently challenging in a quantum mechanical sense, and I will not talk about those today, but I will talk about the rest of these. Line widths and shifts are things that Hans Liebe measured quite a bit in the millimeter wavelengths, and I'll show you measurements we've made in that range, as well as in the oxygen A band. And then for many of the lines, we are now also doing corrections for line narrowing and speed dependence. So this is a generalization of the Voigt profile that includes corrections for the fine motions and of molecules within the gas phase. And then we also have these phenomena that occur when you have a collision during the absorption period. You can either, the collisional angular momentum can actually shift the absorption from one line to another, and we call that phenomenon line mixing. It was originally intensively studied in the millimeter wavelengths, but now is a focus in optical and infrared measurements. And then all of that goes into what we call the resonant absorption, which you think after all that you'd be done, including all of these effects. But what we find is that when we model all of these effects, the bands still have unaccounted for absorption that's due to binary pairs of two oxygen molecules interacting while the photons are passing through the sample. And we call that either continuum or collision-induced absorption in our applications. And so here I repeat my cartoon diagram and show that now when you have these two molecules that are in proximity to each other, the fields that they exert on each other or the impact of them actually physically hitting each other can change the selection rules, and you can actually get these double transitions. So this is now that singlet delta band in the infrared and the A band. You get transitions that have two photons moving. Basically, both of these molecules undergo a transition to their excited spin state at the same time with a single photon. those can occur in the orange and the red parts of the spectrum at 580 and 630 nanometers. And they don't correspond to anything on this diagram here because they take two molecules, and this is a single diatomic molecule, but they are double transitions to these levels here, the A and B levels. And we were able to probe these in the same instrument that we made the emission measurements with, except now we put a high pressure gas cell and a laser driven light source on the outside of the system. And when we focus the light through the cell and put in pressures up to 116 bars, we were able to see the pure collision-induced absorption features and measure their shapes, which a lot of the previous studies only looked at the total intensity of these bands. However, the applications for atmospheric work are getting finer resolution, and so there's interest in getting the entire structure of these shapes. And also we were interested in understanding this same phenomenon that it occurs underneath the resonant line of the A band and the singlet delta band. And so we wanted to use this system to study both the optical and the infrared collision-induced absorptions. And so from that same set of spectra where we got optical measurements in the red, we also were able to get new estimates for the feature underneath the oxygen A band, which is near infrared or the deep red. And there's been previous work done on this band as well. And what we're showing here in purple is data with the resonant line model, our best model at the time, removed so that you can see just the non-resonant absorption. And what's shown in the black trace and the blue trace are representations from different models for the effects of line mixing in the resonant lines and for the air CIA that we extracted from atmospheric measurements. And the way these are presented, there shouldn't be much physical difference between them. So we are still sort of in a large uncertainty range in understanding this phenomenon. It shows up in absorption residuals from infrared spectra of the atmosphere. You see the absorption spectrum of oxygen in the atmosphere on top, and then the residuals due to our different models. And mainly we made things a little better out here past what's called the band head in the R branch, and the center of the band improved somewhat too. But this is a really challenging measurement. The experimental efforts are still ongoing with my laboratory as well as laboratories at Caltech and NIST. So I mentioned that the apparent signal for collision-induced absorption is dependent on the model we use for line mixing in the resonant absorption. And so there are theory in blue here and previous measurements from Adriana Prodoy-Cross that modeled the line mixing in the oxygen A band. And here's the mathematical model. There's supposed to be an animation there. Oh, I have to go backward. Thank you. So the line mixing model used in the theory in blue here included every interaction between every type of line in the band. There's a P branch and an R branch, and within each one of those, there are doublets that are P-type and Q-type transitions. And what we found in this study was that a majority, the yellow features here, of those interactions were minor, that they were perhaps the theoretical values might have been skewing our model. And so we applied Occam's razor and used the most important values, which are what we call nearest neighbor interactions, the P branch, PP type transitions interacting with other PP transitions, and then the PQ interacting with other PQ, and similarly in the R branch. And this allowed us to get a to reduce the theory to mimic the experiments of Prodoi-Cross and the measurements we were getting at that time. And this work was published 3 years ago, but like I said, the work is ongoing. We found already in the last 3 years that we do need these yellow boxes because they become really important in between the P and the R branch. And so in order to get the collision-induced absorption right in that region where there really are no resonant lines, we need to bring back the information that we had deleted from our model in this previous iteration. And that work is now published just this last year in 2020. And we believe that the theory in these regions is only marginally accurate because of the need to develop the interactions for line mixing. They ignored the spin effects within oxygen, which of course are the primary effects oxygen has with radiation. And to think that they aren't relevant during collisions is it's expedient, I would say. They were able to develop a theory, but they basically treated it like a regular diatomic. And so we're working our way towards a pseudo-theoretical solution. And we hope that theoreticians will revisit these line mixing models that to include the spin associated with spin changing collisions in the gas phase. And so moving from the near infrared right past the mid infrared where there's very little oxygen absorption, I jumped right back into the millimeter, submillimeter, and show you again the drawing that I mentioned for our terahertz line position measurements. But now I'd like to talk a little bit about the line shape measurements we made during that time. And here's one of our millimeter, actually this is a submillimeter source, works at 2.5 terahertz. The radiation is produced in multipliers inside these blocks, which are pumped by amplified W-band light. And the radiation comes out of this horn, which you can see reflected off of our off-axis paraboloid here. And this is what we would sit next to a gas cell. So in order to measure the line shapes accurately, we did Zeeman modulation to remove baseline, and that gives them a fourth derivative type shape if you've matched the Zeeman splitting well to the line width. And so you see these interesting multi-peaked features that are all oxygen absorption. You can think of the satellites as different end states of the molecule in the magnetic field. And the first two measurements at 118 gigahertz and 230 gigahertz were made specifically to support the microwave limb sounder mission, which measures these lines in emission from the Earth in the limb, and has been doing that for 16.5 years now. The third line, we could achieve pretty good signal and noise, so we measured it in order to get a more comprehensive data set. And you can see that the values are fairly typical for oxygen and not too far out of the range that people like Hans Liebe got in the past. However, when you do intercomparisons of the literature, you see that there's quite a bit of variability in with respect to 10 to even 20% differences. And missions like the microwave limb sounder have enough fidelity in their retrievals that they actually want and need 1% type precisions on these line shape factors. So we worked hard to get that for the main isotope, and we also integrated for the necessary length of time to get those types of statistics for the oxygen 18 isotope. I think it came in around 4%. The oxygen 18 is not shown on this graph. So even though the agreement wasn't great with literature at the time, it didn't take long for my Russian colleagues to repeat many of these measurements. They regularly check the results that come out of my lab. And typically they make better measurements even. They're very good and precise. And so when you look at models like MPM in their present form, you'll see measurements from my laboratory as well as from the Russian laboratory. Typically, my laboratory is one of the only ones doing temperature dependence of these parameters, though, which is quite useful for atmospheric retrievals. There was also interest in water broadening of oxygen bands. The measurements done in the A band were perhaps spurious, noisy, and so we built a static gas cell and made it Zeeman modulatable, and we attached a cold finger to the cell that allowed us to precisely control the water vapor within the system. And that gave us a stable measurement over long integration times that allowed us to then measure the effects of water vapor on the line shape of oxygen. And we saw at low J a difference between the rotational band and the 60 gigahertz band, which is spin changing collisions, and not that it has rotational levels, but the transitions don't change the rotation. And but at higher J's, they converge, and they also then agree with other bands like the Raman measurements of the vibrational band. And this oxygen A band study that I mentioned was part of the motivation, is shown to be an outlier in those measurements. And as part of this effort, because the 60 gigahertz band is used for temperature sounding in the atmosphere, and because our atmosphere is moist, Eli Maurer showed the sensitivity of that band to variations in the water broadening parameter in this study. And so it does affect the brightness temperature you derive from the wing of the oxygen band, depending on the assumption you use for broadening. Finally, I'd like to tell you about non-resonant absorption measurements that we've done in the radio. The GPS radio occultation group at JPL was looking for anybody who would make measurements, precise measurements and accurate measurements of the refractivity of air. And I got involved. We had Georgia Tech, Paul Steffa's group, build us this resonator, a cylindrical resonator cavity that the dimensions produce the primary resonances with high quality factors at exactly the transmit and receive frequencies of the GPS satellites. And also other resonances, higher order longitudinal modes, can be used as sensitive probes of absorption and refractivity. And so we expected to get good refraction measurements out of this system, and indeed our precision is very high. However, there are some calibration things that I was not ready for, and luckily now we have a graduate from Paul's group, Alex Akins at JPL, who is helping me work through some of the systematic things to correct the refractivity, and also to understand the interesting oxygen absorptions that were observable with this high sensitivity system. Those are shown on the left here. You can see that this is a very weak feature. The scatter is significant. However, as you increase the density, there's definitely a trend. I've included other temperatures on here, so there might be some skewing due to temperature dependence of these. But these linear models of these two absorption, or of these two resonator frequencies, as well as two more at higher frequency, are enough to look at the model that Hans Liebe developed that's used in MPM and AM and a number of other atmospheric models. And I'm not 100% sure I've calculated the model correctly myself in my spreadsheet, but at first blush, it looks like it goes right through our data, and perhaps with some inconsistency at the higher frequency here, which is actually coincident with measurements used by Hans when he made his model, measurements from the early 1980s. And so we're looking carefully at these measurements here where we have a direct comparison. It's my understanding that the lower frequency measurements are novel, and maybe this community can tell me otherwise, but previous information below 2 gigahertz, I think, is mostly derived empirically from the atmosphere. And Hans Liebe's model was actually rated, he gave its limits as 2.5 gigahertz up to many hundreds of gigahertz. So he actually didn't say that his model would be good at these frequencies, but our measurements show that it is actually quite good there, and that with just an adjustment of the width of the zero frequency feature, that you can actually get through all of our data points. However, this may adversely affect the model at higher frequency, and we're still looking into that. I am low on time, so I'll just quickly say that we have a lot of work to do still. The CIA and continua are works in progress. Line shapes perhaps will never be completely done, but I'd like to come back to the intensities in my future work. There's a lot of quantum mechanical selection rules that I've taken into account in my working model. I won't go into detail here other than to say that there's magnetic G factors, magnetic dipoles, and then also quadrupole elements in this model. And we have quite a bit of data to compare intensities to. This was work done to understand the information in the HITRAN database. And I'll finish up my talk by acknowledging contributors, primarily Shanshan Yu, who developed the resonant line model, and Alex Akins, who's working right now on the resonator data that I just finished showing you. Chip Miller, Holger Mueller, Harshal Gupta, Tim Crawford, Kian Sung, Vivian Payne, Dave Long, Chris Benner, and Eli Lauer are all critical persons who provided input to all of the papers I talked about today. Herb Pickett passed away a few years ago. I wouldn't have been able to begin this work without his inputs, and he worked on oxygen for his entire career and was a contemporary of Hans Liebe. So I attribute much of what I've learned to Herb Pickett and want to acknowledge that now. Finally, the work supported by Jet Propulsion Lab, Caltech, and NASA, particularly Ken Jux at the NASA program management level, has supported pretty much all of the laboratory work. And I want to thank URSI again and the Hans Liebe Foundation, NSRM for having me, and Al Gazewski for giving me this opportunity. Thank you.
Thank you so much, Dr. Drouin, for an outstanding discussion of this critical work, really, that underlies our being able to use these models reliably. Thank you so much. I'm going to say we have time for about a question, but there will also be the opportunity for a meetup session with Dr. Drouin at 3:10 p.m. this afternoon, if you'd like to go into any details. So I encourage you to join that session. And we have time for about one question now before we'll have to go on to the break between now and the next session. So anyone? Okay, I'm just going to say one thing then before we go on, and I'm very excited about the continuation of your work, the application of this to additional studies, the continuum absorption of water vapor, for instance, which still remains an outstanding issue, and the further refinement of the database. This is such a profound connection that your work is providing to quantum physics, as well as to our application work. So thank you very much, Dr. Drouin.
You're welcome.
We're going to conclude our 8th Hans Liebe lecture now. And again, I want to encourage you to join Dr. Drouin at 3:10 p.m. today, Mountain Time, for additional questions. And thank you all for attending.